Hello, everyone, and welcome to Bookercast, the podcast where books come to life.
And I'm so excited to dive into another amazing story with all of you.
Whether you're a bookworm or just love a good story, this is the place for you.
Every episode, we explore incredible books, talk about their stories and characters, and share insights that'll make you fall in love with reading all over again.
All right, let's not keep you waiting any longer. Get comfortable, and let's jump right into it.
Sounds good.
All right, strap yourselves in, folks. We're diving deep today into a concept so mind-boggling, it'll leave you questioning everything you thought you knew about reality. That's right, we're talking multiverses. Brian Greene's The Hidden Reality explores this very idea. It delves into the different multiverse theories proposed by modern physics, and trust me, it's a wild ride.
It really is. What makes this book so compelling is that it doesn't shy away from the philosophical implications either. What does it mean for our universe to be just one of many? What are the limits of our knowledge? Big questions, for sure.
Greene wastes no time grabbing our attention, right? He opens with this question: what if everything we see, everything we know, is just a tiny sliver of a much vaster hidden reality?
It's a powerful image, isn't it? It challenges us to redefine what we mean by universe. We tend to think of it as all-encompassing, but what if there are realms beyond our comprehension?
Whoa, hold on a minute. So we're not just talking about other planets or galaxies here. We're talking about entirely separate universes, each with their own unique properties.
You got it. And Greene lays out 9 different multiverse theories in the book, each with its own mind-bending characteristics. Some suggest universes separated by unimaginable distances, while others posit universes right next to ours. Some even challenge the very notion of location itself.
Okay, my head's spinning already, but let's try to unpack some of these theories. The first one, the quilted multiverse, seems like the most straightforward. How does that one work?
It stems from the idea of infinite space. If space goes on forever, then every possible arrangement of particles, every combination you can imagine, well, it has to repeat somewhere.
You mean countless regions out there identical to our observable universe, infinite copies of ourselves, each living out a slightly or maybe wildly different life.
Precisely. And what's fascinating is that this idea arises from basic logic and the known laws of physics. It makes it surprisingly plausible, even if it's hard to wrap our heads around.
So there are infinite me's out there, making different choices, having different experiences. Does that make my choices here less meaningful?
That's a great question. It delves into the philosophical heart of the matter. Does this knowledge diminish our actions, or does it empower us, knowing that every possibility is being explored somewhere?
Heavy stuff. It makes you think, doesn't it? Okay, so we've got infinite versions of ourselves in the quilted multiverse. What's next on this multiverse tour?
Let's journey back to the very beginning of our universe, the Big Bang. Specifically, a puzzle presented by the cosmic microwave background radiation.
The afterglow of the Big Bang, right. Isn't that supposed to be incredibly uniform, like a smooth blanket of energy?
It is, and that's the problem. According to the standard Big Bang model, different regions of the early universe were too far apart. They simply wouldn't have had time to interact and reach the same temperature.
I see. It's like having a room full of ovens that all magically heated to the exact same temperature without ever being turned on. Something doesn't add up.
Exactly. This is known as the horizon problem, and it throws a wrench into traditional Big Bang cosmology. But don't worry, there's a potential solution. Inflation.
Inflation. That rings a bell. It's like the universe hit the gas pedal in its first moments and expanded at an insane rate, right?
That's it. In the tiniest fraction of a second after the Big Bang, the universe expanded faster than the speed of light.
Wait, faster than light? Isn't that impossible?
It is for anything moving through space, but the fabric of space itself can expand at any speed. That's the key to solving the horizon problem. Imagine those distant regions were once close enough to interact, to reach a uniform temperature, before inflation stretched the universe apart.
So it's like taking a tiny drop of ink, perfectly mixed, and then stretching it out over a giant canvas. The ink is still spread evenly, even though the canvas is now huge. But what could have caused such an unimaginable expansion?
The driving force is thought to be a quantum field called the inflaton field. It has these crazy properties like negative pressure and repulsive gravity.
Repulsive gravity. Instead of falling down, I'd be flying up.
That's the idea. Now imagine this. Some physicists believe that inflation might not have been a one-time event. They think it could be happening continuously, giving birth to a multitude of bubble universes.
Whoa, so while we're sitting here, other universes are popping into existence like popcorn kernels. each with its own unique set of physical laws.
That's the mind-boggling picture painted by the inflationary multiverse theory.
Okay, we've got infinite copies of ourselves in the quilted multiverse and these bubble universes popping up all over the place. My brain needs a break. What else does Greene have in store for us?
Hold on tight because we're about to enter the realm of string theory and the concept of brain worlds. It's going to get even wilder.
String theory and brain worlds. Bring it on. I'm ready for the next level of cosmic craziness.
Okay, so string theory. This is where things get really interesting. One of the things string theory suggests is the existence of a brain multiverse.
Brain multiverse. Okay, I'm all ears.
But first, a quick recap on string theory itself. Instead of tiny point-like particles like electrons and quarks, string theory says everything is made of these incredibly tiny vibrating strings.
I always picture them as like little cosmic guitar strings, vibrating at different frequencies to create all the different particles and forces we see in the universe.
That's a pretty good analogy, though, of course, string theory is far more complex than that. And here's the kicker. For string theory to work mathematically, it needs more than just the 3 dimensions we experience every day.
Wait, more dimensions? You mean beyond length, width, and height? I don't see any extra dimensions in my living room.
That's because string theory proposes that these extra dimensions are curled up really, really small, so tiny that we can't perceive them directly.
So like imagine a garden hose. From far away, it looks like a one-dimensional line. But up close, you see it has this curled up second dimension. Are you saying that space itself could have these tiny hidden dimensions curled up per minute?
Exactly. And this is where we get to the idea of brain worlds. Picture our 3-dimensional universe as a giant membrane, or a brane, floating in this higher dimensional space. Now imagine other branes, other universes, also floating in that higher dimensional space, each potentially with its own unique set of physical laws.
So like a cosmic loaf of bread, with each slice representing a different universe, each with its own unique flavor. Pretty wild.
It's a mind-bending concept for sure.
But if these other brain universes are out there, how would they interact with each other? Could we ever detect them?
That's where gravity comes in. One of the exciting things about string theory is that it suggests gravity might be the only force capable of leaking between these branes.
Leaking gravity. So we might not be able to see these other universes directly, but we might be able to detect their presence through their gravitational influence.
Precisely. Like a subtle tug or ripple in space-time that hints at something massive lurking nearby in another dimension.
Talk about cosmic hide and seek. Now, I know Greene also delves into the idea of cyclic universes where the cosmos goes through cycles of expansion and contraction, kind of like a cosmic heartbeat. It's a fascinating concept that's been around for a long time, right?
It is. It's an ancient idea found in various cultures, this idea of a universe that expands, collapses, and then is reborn again. And string theory provides a potential mechanism for this, the collision of branes.
So instead of just one big bang, there could be a series of them, each triggered by these brain collisions.
Exactly. Imagine 2 brains colliding, releasing a tremendous amount of energy, creating a new Big Bang, a new universe.
Yeah. So universes being born, expanding, colliding, and giving birth to new ones. It's an endless cycle of creation and destruction, cosmic reincarnation on a grand scale. But doesn't that run into a bit of a snag with the whole entropy thing? You know, the second law of thermodynamics? Doesn't that say that disorder always increases over time? Would these cycles eventually just lead to a cold, chaotic mess?
You're right. The second law of thermodynamics does pose a challenge to the idea of infinite cycles. Each new cycle would inherit the entropy, the disorder, of the previous one. However, brain collisions might offer a workaround, leading to a cyclic multiverse with no beginning or end.
So a universe with no ultimate beginning or end, constantly renewing itself. I like that idea. It's kind of hopeful in a way. But let's move on to another big mystery that Greene tackles: the cosmological constant and the accelerating expansion of the universe. This is some seriously mind-blowing stuff.
It is. For a long time, we thought gravity would eventually slow down the expansion of the universe. But then, in the late 1990s, astronomers made a startling discovery. The expansion isn't slowing down, it's speeding up.
It's like throwing a ball in the air, and instead of falling back down, it just keeps going faster and faster. What's fueling this cosmic joyride?
The prime suspect is dark energy. This mysterious force permeates all of space, acting like a sort of anti-gravity pushing everything apart.
So it's like a cosmic tug of war between gravity pulling things together and this invisible dark energy pushing them apart. But how does the cosmological constant fit into all of this?
The cosmological constant is basically a measure of the strength of this dark energy. It's a term that Einstein first introduced in his theory of gravity when he thought the universe was static and unchanging. He used it to balance out gravity and keep the universe from collapsing.
So Einstein basically invented this cosmic anti-gravity force, then dismissed it as his biggest blunder when he realized the universe was expanding. And now it's back to explain the accelerating expansion. The universe works in mysterious ways, that's for sure.
It does. But the cosmological constant presents a real puzzle. See, quantum field theory, our best theory of the subatomic world, predicts a huge amount of energy in empty space. This vacuum energy, as it's called, should be so strong that it would rip the universe apart.
So we've got this cosmic pressure cooker that should have exploded long ago, but here we are, sipping our coffee and pondering the mysteries of the universe. Clearly something's not quite right with our understanding.
That's where the landscape multiverse comes in. String theory suggests that there could be a vast landscape of possible universes, each with a different value for the cosmological constant.
So like a cosmic menu with a wide array of cosmological constants to choose from. And we just happen to live in a universe where it's small enough to allow for stars and galaxies to form. Talk about luck.
Is it just luck? Or is there some deeper principle we haven't grasped yet that explains why we find ourselves in a universe with the particular cosmological constant we observe? That's a big question that cosmologists are grappling with.
It seems like every time we answer one question about the universe, 10 more pop up. But that's what makes it so fascinating, right? This never-ending quest to understand our place in the cosmos.
Exactly. The journey is just as important as the destination. And even if we never definitively prove the existence of these other universes, exploring these ideas expands our understanding of what's possible.
It's a humbling and awe-inspiring experience to realize just how much we still don't know. But here's a question. How can we even talk about these multiverses scientifically if we can't directly observe them? How can we test these theories?
It's a valid point. How can we call something science if it's beyond our ability to directly observe and test?
It feels like we're venturing into the realm of pure speculation, right?
That's a criticism that Greene addresses head-on in the book. See, in traditional science, we rely heavily on observations and experiments. We formulate hypotheses, test them, and gain confidence in our theories if the results align with our predictions. But even in well-established areas of science, there are many concepts that we accept as real, even though we can't directly observe them.
Give me an example.
Think about the interior of a black hole. We can't send a probe in there and get data back, yet we have a pretty solid theoretical understanding of what happens inside based on Einstein's general relativity.
Ah, I see what you mean. So we're applying that same principle to the multiverse. We have these multiple theoretical frameworks pointing towards its existence, even if we can't directly see it.
Precisely. It's like having different pieces of a puzzle from different areas of physics that seem to fit together. They suggest a larger picture, even if we can't see the whole thing yet.
And then there's the anthropic principle, which often comes up in discussions about multiverses.
Ah, yes, the anthropic principle.
Isn't that the idea that the universe is fine-tuned for life? That all these physical constants are perfectly set to allow for our existence?
That's one way to think about it. But the anthropic principle can also be applied to the multiverse to make testable predictions. Let's go back to that cosmological constant problem we were talking about.
The one where quantum field theory predicts a huge vacuum energy that should have ripped the universe apart ages ago.
Exactly. So how are we even here? Well, Steven Weinberg used the anthropic principle to make a prediction about the cosmological constant.
Okay, how did he do that?
He reasoned that if there is a multiverse with varying cosmological constants, then we must inhabit a universe where it's small enough to allow galaxies and stars to form. If it were larger, we simply wouldn't be here to observe it.
So he basically said, hey, if we exist, the cosmological constant can't be too big or we'd be toast.
Precisely. And what's remarkable is that he made this prediction before astronomers discovered the accelerating expansion of the universe, which implies a small, non-zero cosmological constant.
Wow. So he predicted this cosmic anti-gravity force before we even knew it existed.
It's a pretty amazing example of how the anthropic principle, even though it's often viewed with skepticism, can actually lead to testable predictions.
That's incredible. But I know there are still some big challenges when it comes to understanding multiverses, right? Like that measure problem you mentioned earlier.
Ah, yes, the measure problem. That's a thorny issue. It boils down to this. How do you compare probabilities in a multiverse with an infinite number of universes?
If everything that can happen does happen in some universe, how can one outcome be more likely than another?
It's a real head-scratcher. It's pushing physicists to develop new mathematical tools and ways of thinking about probability in the context of infinity.
So it's a cosmic math problem, waiting for its Einstein to come along and crack the code. Makes you realize that even with all our advances in science, there are still vast realms of the universe, and perhaps beyond, that we're only beginning to grasp.
Absolutely. And Greene doesn't stop there. He dives into even more mind-boggling ideas, like the possibility of simulated universes created by advanced civilizations.
Whoa, simulated universes. You mean like we're all just living in a giant computer simulation designed by some super intelligent being?
It's a trippy thought, isn't it?
Makes you question everything you thought you knew about reality.
And then there's the ultimate expression of the multiverse idea, the ultimate multiverse.
The ultimate multiverse. Okay, lay it on me.
It proposes that every conceivable mathematical structure exists as a real physical entity.
Whoa, slow down there. So if you can imagine it, it exists somewhere out there in the vastness of reality.
That's the idea. It's a truly mind-bending concept that challenges us to reconsider the very nature of existence itself.
It's incredible how these ideas push the boundaries of what we thought possible, forcing us to confront the limits of our understanding.
Exactly. And while we may never definitively prove the existence of other universes, exploring these ideas expands our imagination and opens up new avenues of inquiry.
It's been quite a journey today, exploring the mind-boggling world of multiverses.
It really has. Brian Greene's The Hidden Reality is a captivating exploration of some of the most profound questions in cosmology and physics.
It makes you realize just how much we still have to learn about the universe, or should I say universes.
And that sense of wonder, that drive to explore the unknown, is what makes science so exciting.
Well said. A huge thanks to our listeners for joining us on this deep dive into the hidden reality. We hope you've enjoyed it.
And until next time, keep looking up and keep questioning everything. There's a whole universe, or perhaps even a multiverse, waiting to be explored.
That's it for this episode of The Deep Dive. We'll see you next time.
And that's a wrap for today's episode of BookerCast. We hope you enjoyed diving into it as much as we did. Thank you so much for spending your time with us. Your support means the world, and we can't wait to hear your thoughts on this episode.
Don't forget to subscribe, hit that like button, and share this episode with your fellow book lovers. And let us know your thoughts in the comments below. We love hearing from you. See you in the next deep dive. Bye for now, and happy reading.